couple of handouts that are being distributed now so that people can follow along. I think I'll be formally introduced before I start actually. Anyway, do people watch Jeopardy anymore? Okay, good. I mean, this would actually, I will need this tune later.
It is hard to contain the depth of Noam Elkies' resume in just a few sentences. His accomplishments are numerous, receiving a perfect score on the International Mathematical Olympiad at age 14, winning the Putnam competition at age 16 and then twice more, receiving a PhD from Harvard at age 21, and becoming the youngest professor to receive tenure at Harvard at just 26. He is also extremely talented in many other areas. He is a US chess national master, a world chess solving champion, and a composer of both music and chess problems alike. His musicianship was described as an extraordinary gift by the former director of the Harvard Glee Club, and he'll be demonstrating some of that ability during the lecture tonight. Without further ado, RSI 2019, please give a warm welcome to Professor Noam.
Thank you very much. Thanks for inviting me back here. Welcome to, well, MIT, the United States for many of you. Good luck with your own coming research experience. For this talk, I am going to be, I asked the one main, what do you call it, audiovisual, piece of audiovisual equipment that I need that's rather unusual for a talk at RSI is a piano, and it does have to be an acoustic piano, even though there are some very good digital instruments for reasons that will become clear at a specific point later. And this is to, I mean, the one thing that he did not mention was the title of my presentation, which is G sharp, A flat, and depending on which version of this talk you're hearing, either Euclidean algorithm or continued fractions. And given the kind of background that you've heard or read about, you're probably not surprised that I'm often asked, as indeed I was asked at the dinner just about an hour ago, about the relationship between mathematics, you know, the world of integrals and other such calculations, and of music. And it must be admitted that most of the connections that people draw or try to draw don't go much deeper than this silly visual pun. But there are few places where scientific and specifically mathematical thinking can tell us some unobvious things about music, and one of these is the theme of this talk. I wrote specifically G sharp and A flat, but on the piano, G sharp and A flat are just one example of two or more names for the same note. In fact, this is this one and its equivalent notes elsewhere in the pattern of white and black notes here are the only ones that have only two names. Most have three, like middle C or central Do is also B sharp and is also D double flat. And likewise, most notes have actually three different names without resorting to triple sharps and quadruple flats, etc. And this is one manifestation of a rather strange bit of strange-looking bit of structure that's universal in Western music and represented by what you see here on the keyboard. So if you go up the keyboard, and if you don't have absolute pitch, you can't tell where I started this, what's called chromatic scale, going up from, as it happens, C, but it would have sounded the same if I started anywhere else. And yet, you'd think, therefore, that this structure should be represented by, just a sequence of equal keys. And yet, the keys on the keyboard, on every keyboard that's ever been, well, almost any keyboard that's ever been made, certainly any keyboard in the last, practically any keyboard in the last few centuries, has the keys divided in the same pattern. The distance between two consecutive notes is always the same. And the pattern repeats after 12 of them. And there's always 7 white notes. If you're counting, count at 8, but that's because the last one is already the beginning of the next cycle. So 0, 1, 2, 3, 5, 6, 7. What? 1, 2, 3, 4, 5, 6, 7. And then again, the one of the next one, and the remaining notes, 5, and they're always in this pattern. And why is that? What causes this? What is the underlying structure that's represented by this and also represented by music notation? The white notes, the fact they're white and the others are black, that's not universal. I mean, if you play in a harpsichord, usually the smaller keys, the raised ones are white or at least a lighter color, and the larger ones are black or brown or beige or ecru or whatever. But the pattern is universal, and it corresponds to the notation for notes. Each one of the white notes, the larger notes, has several names, but one of them is just a letter or a plain syllable. Do, re, mi, fa, sol, C, D, E, F, G. And there are 7 of them, do, re, mi, fa, sol, la, ti. And the others you have to make a modification. So you call this either G sharp, that is to say it's a note just above a G, or A flat, la bemol, sol diez, the note just below la, or A, depending on which music notation system you're used to. But where does this come from? And the answer turns out to involve a rather remarkable collection of, confluence of everything from, history and even philosophy of Western thought and physics and actual physics and mathematics, arithmetic, etc. And I've chosen to introduce it, especially since we're starting here with, this is even though many of you are musicians, this is a summer program in science and mathematics. So I'm going to start with the science and math part, and then I'll draw the thread that connects this to music. So for the first, whatever length of this talk is needed to go through this short handout, there won't be any explicit music, and this will be all about the Euclidean algorithm, which was, for a long time, as some of you already heard at dinner, I'm a bit of a dilettante about, the strange origins of various words in our language. Algorithm is, anybody know where algorithm comes from? Oh, good.
Al-Khwarizmi.
Wow, what's Al-Khwarizmi?
Iraqi mathematician?
Or
like his Arabian, I think.
I thought he was actually Persian, but one way or another, which would be Iran and Iran. But yes, it's from, he was a mathematician who lived in the town of Khwarazm, and somebody from Khwarazm in Arabic would have been known as the Khwarizmi, there being Al, so algebra, almanac are all from, aluminum is the one counterexample. Aluminum is not in the Arabic Al. But the Khwarizmi person was Al-Khwarizmi. And it somehow became modified, corrupted, whatever you want to think about, to algorithm. And he presented this technique, which goes back to Euclid. And for many centuries, when you said algorithm, that was what you meant. You meant that the Euclidean algorithm. It's sort of like the grand progenitor of all algorithms. And eventually, it's sort of like acoustic guitar. We have to say acoustic now, but for centuries, the guitar just was what we now call an acoustic guitar because there was no other kind of guitar. So algorithm was the same. And what does it do? Well, we usually think about it in terms of numbers. You take two numbers and you find their greatest common denominator, the greatest common divisor. And Euclid was the great systematizer of ancient Greek geometry. And for the ancient Greeks, numbers were just a way to compute with geometry. So their main model of what the Euclidean algorithm did was you had two lengths, and this is, I don't really need to draw it here because that's like the first drawing you see there. And you want to find a single length that you can use to measure both of them, if it exists. Two lengths which have a common measure like this are, if the Greeks were looking for a word for that, measuring would be like something like meter, and something that can be measured together by the same common length would be like symphony is something that sounds together. Something that can be measured together would be symmetric, but that word already has another meaning in mathematics. So we use the corresponding Latin word, which is commensurable. So two lengths are commensurable if you can find a single distance which will measure both of them. And in modern mathematics, as soon as we see something like this, we start asking questions like, what kind of relation is this? Two lengths are commensurable if and only if there exists such a thing. So what can you say about this relation? And well, the standard questions about relations is, one of them might be, many of you have seen this already. Okay, more of you have seen this than know what algorithmy was. Does the word equivalence relation ring a bell with anybody? Okay, so if you have never seen this before, this is an example of an equivalence relation, which is, among other things, it's a way of splitting up the set of possible lengths into equivalence classes. Two lengths are in the same equivalence class if they're commensurable. And for that to make sense, you have to check a few axioms. Like you want to check that for all x is commensurable with itself. That's clear, because if x is the same as x, you can use x itself as a common measure. X is commensurable with y if and only if y is commensurable with x. That's easy too. The hard part, as it usually is for these, is showing what's known as transitivity, which is that if x is commensurable with y and y is commensurable with z, that means that x is commensurable with z as well. You see, that's going to be trickier because it's not necessarily the same measurement that you use for x to measure x and y and to measure y and z, right? So you might have to divide this into 5 parts instead of 12. And so what you need is to show that if you can find such a measure for x and y, you can find one for y and z, then there's another one, possibly smaller but not vanishingly short, of positive length, that connects x and z. And again, for us, this is easy because we have algebra, another one of these words, I gave that example before, that we get from the golden age of Arabic mathematics. And algebra tells us, well, if this, I do this calculation also on the handout, it tells us that if I have m lengths of this common distance d and n lengths of this common distance d, well, then the ratio of x to y is the ratio of the same whole numbers m and n. And then there is a bit of algebra that says, well, x over z is x over y times y over z, because the y's cancel out. On the other hand, this is a ratio of two integers, this is the ratio of two integers. They're both rational in the literal sense of being ratios. And the product of two ratios of whole numbers is again a ratio of whole numbers. So that's easy to do with algebra. It was harder for Euclid, both because he didn't have the explicit notion of an equivalence relation, but also because he didn't have algebra, and so he had to give a corresponding geometric argument. But he did that. And let me give another geometric description. I'm actually not going to start a new page. I'm just going to refer to the whole bottom half of the first page here. I mean, if I wrote out a handout, I might as well use it. And basically, you can tile an x by y rectangle with squares. That's equivalent to that rectangle being, to the two sides being commensurable. And the Euclidean algorithm is a way of finding that common length if it exists. And basically it says, well, if you have a common measure for x and y, it's also a common measure for y and x, so you might as well assume that x is no longer than y. If x is as long as y, then of course the best measure you can use is x itself. Otherwise, any measure you can use for x and y, you can also use for x and y minus x. And the Euclidean algorithm basically repeats these two observations. If x is not less than y, if x is bigger than y, switch them. If x is less than y, replace y by y minus x, and keep going. And what Euclid shows, which once you have given this algorithm, is more or less, that's another thing that makes it a classic algorithm. It actually gives you a proof, if you think about it a bit further, that there exists a largest possible, a greatest common divisor, and every other common divisor is an exact fraction of that. Again, this might seem obvious to you because you know algebra, but in fact, that's the way to prove that little bit about arithmetic, that fractions have greatest, can always be brought into lowest terms. That is actually a non-trivial fact, which takes a while to realize because we've all been, we've all learned arithmetic with that assumption. But the Euclidean algorithm, among other things, is a way to prove some basic facts about arithmetic, and it's also a way to find this minimal, this common measure. And it can be described in several alternative ways. I give you the rectangle picture at the bottom of the second page. You take your x by y rectangle. If it's a square, you're done. If it's not a square, one length is larger than, one side is larger than another. So take out the square and repeat on the smaller rectangle. And one of two things will happen, if you believe in the law of the excluded middle. Either the algorithm will terminate, which means that at some point you'll find that x is equal to, the new x is equal to the new y, and so when you subtract one from the other, you end up with 0. Or it will never terminate, and then the two numbers are incommensurable, and the quotient of their length is irrational. Again, not in the common sense of the word irrational, but literally meaning it cannot be written as a ratio between two whole numbers. So that, of course, can happen. Well, of course, to us, because we have been, inculcated with this from our grade school days. It was actually rather a surprise, in fact, a shock to one thread of Greek mathematics that that there could be pairs of incommensurable numbers, and a lot of their geometry was based on, find a common measure for two distances and use that in the proof. And at some point, they had to come to terms with the fact that, no, typically there isn't a common measure, and you have to go a long way towards inventing modern calculus to, unfortunately, Eudoxus never quite got all the way to the end of that, so it took us another millennium and a half. But you need to deal with limiting processes in some sense, the method of exhaustion, to handle incommensurable lengths. And the easiest way for a length to be incommensurable, for a pair of lengths to be incommensurable, well, it doesn't make sense to say a single length is incommensurable. Incommensurable with what? But for two lengths to be incommensurable is for the first rectangle you get when you take out the square to be similar to the original one. Because if this rectangle is similar to the first one rotated, well, that means that when you keep doing this, you will always... Now, of course, this picture doesn't look right. It looks closer to being right in the handout. It's often been noted that geometry is the art of reasoning correctly with figures drawn incorrectly. And I think I've made sure to at least satisfy one of these two requirements here. But at any rate, a rectangle which is similar to the rectangle you get by taking out the biggest possible square is often known as, oh God. Well, yeah, Fibonacci has to do it, but you're like 2 or 3 steps ahead of me. What's the rectangle called? Golden rectangle, thank you. The ratio between the two sides is the Gordon ratio. And if at any point you imagine that the rectangle you have reached was actually a square and not a very tiny Gordon rectangle, then you work your way back and indeed find that the rectangle you started out with has 2 consecutive Fibonacci numbers for its sides. So I've given away, well, because one of you has already given away the answer to one of the puzzles here. For the other puzzle, so by now you have pushed me all the way up to page 4. And the other puzzle is to do the same thing with the example of an irrational number that everybody has heard of first, even though it might have been the second one that the Greek got, which is the square root of 2. So for the square root of 2, what happens is if you have a rectangle which is 1 by the square root of 2, or as the Greeks would say, the side and the diagonal of the square, then you still can only take out 1 square, but then you get a very thin rectangle, well, not very, but thin enough, that you have to take out 2 squares before you have to switch the 2 sides. And it turns out when you have taken out the second square, you get something that's not quite as thin as this looks, and in fact it's exactly similar to the rectangle you start out with. And that's not too hard to do with algebra because you've learned the trick of rationalizing the denominator. It's a bit more interesting to do it with Greek-style geometry, but it does give you one proof that the square root of a different kind of proof that the square root of 2 is irrational without having to worry about even and odd numbers and those tricks. And if you play the same game of imagining that one of the rectangles you've gotten along the way is actually a square and work your way back to get an approximately 1 by square root of 2 rectangle, you end up with the solutions to the so-called Pell equation, which is instead of having m squared exactly equal to n squared, which is what it would be if you had m over n being exactly the square root of 2, you get the next best thing, which is in some sense better because it's actually possible. You can make the difference equal plus or minus 1. And there's an infinite sequence of solutions for that. The corresponding equation here, which I must confess I didn't realize until looking back at my solution like halfway through the exam, showed up on that International Math Olympiad in 1981, was that the same equation, m squared minus mn minus n squared equals plus or minus 1, characterizes consecutive pairs of Fibonacci numbers. Okay, So before we say what this has to do with music, let me give one additional interpretation of what we have done here from something closer to our modern point of view where we are allowed to think about fractions. So you start with your lengths x and y, and you are allowed now to think about the ratio. We call it R for ratio. So what are the two operations I allowed you to do? You can check whether R is 1. You can check whether x equals y. You can switch x and y. What does that do to R? Takes R to 1 over R. Right. So 1 over R is x over y. And you're allowed to subtract x from y. What does that do to R? Yeah, it subtracts 1 or takes away 1. Right, so the next thing you can do is to take y and change it to y over x, and that's equal R minus 1. And if that's still bigger than 1, to say if the resulting numerator is still bigger than the denominator, you can change that to R minus 2, R minus 3, etc. And in general, you can take R minus n, where n is the biggest number, the biggest whole number you can subtract. So what we are saying then is you'll take any number R, you will write it as n plus some new number that's between 0 and 1. And unless it's 0, now the new y is smaller than x, so you switch them, so you write it as 1 over something that's bigger than 1. So there'll be the first quotient here, and then you repeat the procedure. You say n2 plus, you have some number, you subtract off the biggest whole number that will fit, plus 1 over, and then, oops, sorry, this plus should go here, n3 plus dot, 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 and eventually one of two things will happen. Either one of the numbers you get here will fit exactly, and you'll get a so-called finite continued fraction, n1 plus 1 divided by a continued fraction of length 1 less than that, n2 plus 1 over, n3 plus 1 over, and so forth, until you get some rational number here. Because that's a rational number, the number before it was rational, right? The previous number plus this is rational, 1 over that's rational, add a new thing. There are more and more complicated rational numbers, but you end up with the rational formula for R, and you found that R is rational. If this never ends, you get an irrational number, you get an infinite continued fraction expansion. So that's what continued fractions have to do with you create an algorithm. And I should also observe that this is actually quite an efficient algorithm in the sense that if you give me 200-digit numbers and I ask you what's the greatest common divisor, normally you don't want to just factor one of them and factor the other one and find the common prime factors, because factoring a 100-digit number is, well, it's not obvious at all that you can do it even with modern computers, because modern computers, they work at, okay, let's do this calculation here. If your computer works at some number of gigahertz, a giga is 10 to the 9th, a hertz is 1 per second. So it can do a few billion operations per second, at least if you're speaking a language where 10 to the 9th is a billion, as opposed to a milliard. And of course, doing arithmetic with 100-digit numbers is not a simple operation, so it will take some output of that. But let's even imagine you could do 10 to the 9th of these per second. How many seconds in a year? Yeah, so it's a reasonable approximation. I mean, it's not really much better approximation than 3 times 10 to the 7th, but it's more memorable. So 3 times 10 to the 7th seconds per year. So we have about 3, or if you like, pi times 10 to the 16th operations per year. A bit more than that if you're willing to dedicate several computers to it. But still, if you have a 100-digit number, there are 50 digits of possible prime factors. You are going to get 10 to the 16th of them every year. You'll be at it for something like 10 to the 34th years. fortunately, starting from Fermat and up to several leading computation number theorists of the past generation or two, we have techniques that will make it possible to factor a 100-digit number in a reasonable time. But change the 100 to 10,000, and you have something that's still intractable, enough so that, I'm not going to promise that 10,000 is the right number, but some sufficiently large but still practical number is what makes your internet communication secure. But that's a different story. But if you give me two numbers and say what's the largest common factor, you can show that in at most 5 steps of the Euclid algorithm, you reduce them both by at least 1 digit. This comes about basically because the 5th power of the golden ratio is about 10. And about the worst thing that can happen, if you can imagine, is if you have the ratio of 2 consecutive Fibonacci numbers, because then each of the quotients is 1. And so if you start with 200-digit numbers and 500 steps, you'll bring it down to nothing. In 500 steps, you're certainly willing to do, even if it takes you, 100 operations or 1,000 operations, because you have 10 to the 9th operations to do in a second. So even, centuries after Al-Khwarizmi, this is still a model algorithm in that it, takes what seems to be an exponentially intractable problem and makes it something you can, do in a fraction of a second and in some sense in linear time, certainly in polynomial time. Okay, so I'm going to switch gears now and start talking about music for a while before these two threads converge. So maybe this is a good time to pause for questions about this. Yeah?
How does this relate to the least common multiple?
The least common multiple? That's a good question. Anybody happen to know the answer? What's the connection between the greatest common denominator and the least common multiple? Yeah?
The product is the product of two numbers.
Yeah, so there's a nice little theorem. It was probably known, at least in some form, to Euclid, although it's a bit harder to imagine a geometric proof of that. But again, Euclid was not, was no idiot, so he probably had it. So GCD of xy times the least common multiple of xy. I'm writing in a different color so I can, at least to some extent, I apologize to the few of you who might be colorblind and can't see the distinction, is equal to xy. So if you know how to compute one of these and you know how to do long division, you can compute the other. Long division is not easy, but it's easier than Euclidean algorithm. So the two problems are basically equivalent. Yeah?
What are continued fractions applicable to other fields than just this type of repeated algorithm?
It's a way of representing a rational number. So it turns out, for example, that not just the Pell's equation x squared minus 2n squared equals plus or minus 1, but any equation of roughly the same form, so like m squared minus 67n squared equals plus or minus 1. Essentially, the best way to solve it is to find the continued fraction of the square root of 67 and stop each time you get as close as possible to as good as possible in approximation. And again, because the Euclidean algorithm is efficient, this is a good way even for finding solutions which can easily have, almost as many digits, well, roughly as many digits as the square root of this number. So this might have an 8-digit solution. So that's one connection. It's also connected to solving certain linear recurrences, but this might be going a bit farther than we want to right now. But there are other connections to this. I mean, Ramanujan and Gauss have their famous continued fractions, so they weren't just computing GCDs. Anyone else? Okay, so what has all of this to do with 12 notes to the octave and G sharp and A flat and all that? Well, where do those where do those sounds come from at all? I mean, the Greeks didn't have pianos. They had something not too far from a piano in some sense. A piano is a very complicated machine, but if you look inside, all that it is you have a finite collection of strings, and all that you're doing when you're playing the piano is you're choosing which ones of these strings you're going to play and how hard, and also how long. So there's only like a few choices, which string it is, or which course of strings, how loud, and how long it's going to be. If you're playing a violin, you have a whole continuous collection of pitches, and you have some other choices like what kind of bow stroke you'll have, and where on the string you're going to bow, what you're going to do with the other hand. But a piano is a reasonably simple instrument, and it's basically made up of about 100 copies of a very simple instrument, which is just the same thing but with a single string, and all you can do is pluck it. And that, of course, we've had for ages and ages. And of course, that's not the only kind of musical instrument, but many musical instruments are the same kind of thing where you have some physical resonating device, and you hit it somehow and then let it go, and it vibrates. And that makes music because it's in the middle of the air. We didn't realize this until much later. And if it vibrates here, it sets the air into vibrations, and these vibrations eventually reach your ear, and then something complicated happens inside, both the physics of your ear and the, biophysics, etc., of your brain, and it actuates something that says F sharp, or whichever note it is. Curiously, by the way, even if you don't think you have absolute pitch, your brain has absolute pitch. But most of us have forgotten when we were very young how to make the connection between a particular neuron and a memory of that particular sound. We only know the ratio, the distances between sounds. Sort of like, if I'd lived in a Hindi-speaking household, I would have been able to pronounce several different kinds of P's. But because I'm not, I'm aware of these distinctions, but I cannot reproduce them. At any rate, so one basic fact about these physical resonators is that bigger ones make lower sounds. Babies squeal, grown men and women, talk at various levels that are, well, what we know as lower sounds. I mean, why is this lower than that and not higher? That's just a matter of convention. And for the Greeks, it was the other way around. The Greeks thought of this as being a higher sound than that. But whatever you want to, because I'm speaking English and not ancient Greek, I'm going to stick with our modern convention. Tubas go and trombones go pa, and flutes go whoop, or even higher than this. And there is a legend that's probably not much more than that, which says that Pythagoras was first moved to investigate this by walking next to an anvil, a metalworking shop where they are hitting anvils, and noticing that if you hit an anvil that's bigger, it makes a lower sound. If you hit an anvil that's higher, it's smaller, it makes a higher sound. But at any rate, however you do it, they eventually settled on an experimental device that's called a monochord. It's not entirely true that the ancient Greeks were like the pure, head-in-the-sky philosophers, and the ancient Romans were the practical scientists. I mean, the Greeks did some experiments as well. And a monochord, okay, so first of all, mono, of course, is for one. Chord is as in vocal cords, not as in this kind of chord. It means string. So monochord, I mean, you could conceivably imagine using a monochord to actually make music, but it was really an experimental device to investigate musical sounds. And I brought with me this because, drawing is not one of my few talents, and so I brought with me a picture from Wikipedia intending to put it on a document camera, and of course there is no document camera in Killian, so I will try to reproduce this description of what a monochord is. So as I said, there is a single string. I'm looking at this head-on, so it's connected to some fixed peg here, and there is a fixed, what do they call it, bridge here, and there is a movable bridge. It can move back and forth, and in the version of the monochord that Wikipedia shows, there is, the string is kept in tension by an actual weight. I think that's a, that may or may not be how they did it originally. I mean, certainly on most musical instruments, you don't have a weight like this, so they make it very hard to hold the violin. And the weight and the tension is actually supplied by stretching the string out between two fixed points. But one way or the other, the string is kept under constant tension, and the only thing that changes is how long the resonating interval is of the string. And the amazing thing that the Greeks found is that not only is it true qualitatively that the shorter the string is, the higher the sound, but they found that exact ratios, like a half or a third or 2/3, make for particularly pleasing combinations. So if the whole string makes this sound, then a string that's exactly 1/2 the length will make this sound. And therefore, a string that's exactly 1/4 of the length, because 1/4 is 1/2 times 1/2, will make this sound. And likewise, you know what an 8 and a 16th would do if you could, measure such distances closely enough. But then, having found it for 1/2, what happens for 1/3? Well, 1/3 looks like this, sounds like this. 2/3 is whatever interval you'd need to go up by a factor of 2 and then down by a factor of 3. So this is 1, 1/2, 1/3, 1/4, 1/5 is this one, 1/6. So small ratios correspond to pleasing sounds, to consonant pairs of sounds. And okay, I mean, because this was still the age of proto-science where, astrology and astronomy were practiced by the same people, yada, yada, yada. There was this whole, philosophical speculation about, the music of the spheres, and, that didn't die down until after Kepler. We're not going to go in that direction any more than we are going to wonder about whether even numbers are male and odd numbers are female, or vice versa, and the Pythagoreans had opinions about that as well. Let's go a few years, a few centuries in the future and see where this actually comes from. So there are several bits of physics here that I have to just, quote without proof. How much time do I have, by the way?
About 40 more minutes.
1-4?
40.
40, okay, good. So I have some time to tell the story. Okay, so it's amazing how much material you can get to in order to actually prove anything. So I mentioned already that the reason that we experience vibrations of this instrument as music, even though you're over there, is that it's vibrations that are conveyed by the air. And this conveyance of vibrations doesn't change the frequency, and at least if you're stationary. We're not going to worry about the Doppler effect here, nor about redshifts and things of that nature. So it's the same frequency, and the question of whether the tone is higher or lower corresponds to its frequency. And it so happens that what we call higher notes are ones that have higher frequency, as opposed to higher wavelengths, which would be the opposite. And the fact that you get out of physics, which in turn has to do with other bits of mathematics involving linear differential equations, etc., but that wasn't realized until later yet, is that if you fix everything except the length of the string, so you fix the material the string is made out of, you fix the weight, you fix some other relevant things like what's the temperature and what's the what's the humidity, etc. The only thing that changes is the length of this interval. The frequency is inversely proportional to the length. So there is some constant that encompasses the physics of the width and the tension, etc., of the string, such that the frequency is that constant divided by the distance. And therefore, if you divide the distance, if you divide the length of the string by a whole number, you multiply the frequency by the same whole number. So like these notes that correspond to half, a third, a quarter, a fifth, and so forth, also have frequencies that are twice, 3 times, 4 times, 5 times, etc., the frequency of the bottom note here. Now, these frequencies are rather large compared to our ordinary experience. I mean, they're not large compared to the kind of numbers I was talking about before, which are like 10 to the 16th. But still, I mean, this note, the standard A440 or La440 that most orchestras tune to, some of them these days tune to 442, but still within 1% of 440. It's called 440 because that's the number of vibrations per second. Ooh, is 4, and we can all make sounds that are 440 or 220 or 110, or if you have a much higher voice than I do, 880. You can all easily make vibrations that are hundreds of times per second. We don't have a direct experience of things that are 100 times per second, right? I mean, that's about 12 notes, and that's, that took most of a second. If I took about a second to go down 53 notes, I don't think you could hear the distance between any two of them as a discrete unit of time. That would have been 2/200ths of a second. And we are talking about 400ths of a second. It's not obvious how you actually measure such a thing. One way that this was done initially is to have a tuning fork and then draw it at a known speed down some, I guess what they used originally was a piece of glass that had some soot laid down on it, like not soot like you wear, but carbon. And what happens, as we know, your what do you call it? Your tuning fork goes back and forth at the same frequency. If you draw it down if you draw it unvibrating down your smoky window, your smoky glass, it just makes a straight line. But if it's vibrating, it makes a sine curve. And then you can measure how many pairs of the sine curve there are per distance, compare that with how fast you have drawn the tuning fork, and that tells you how many vibrations per second are happening. And so you can measure that this note is 440, unless you're measuring it in the next town over, and it's 425, because pitch didn't become standardized until about 200 years ago. But whichever one it is, the tuning fork that will make this sound is exactly half as much, and the one that makes this sound is exactly a third as much. Okay, so nice length corresponds to nice frequency ratios, and frequencies are closer to what actually gets into our ear and what we actually process as music. But still, why does the human ear like ratios that are at pairs of frequencies that are not only commensurable, but approximately commensurable, but with simple ratios? And the answer to that is something that's possibly even less intuitive than the notion of this being defined by something that vibrates at 440 times per second. And that is that each one of these strings here, in some precise sense, which is not, I can't really make precise unless I talk about Fourier analysis. I'm certainly not going to do that here. But in some sense, is vibrating simultaneously, not just at this frequency that you're hearing, but also at the double frequency, the triple, the quadruple, etc. So when I played before, if you believe what I just told you, that means that I actually played, and I had no way of, I did it whether I wanted to or not. I was actually playing this in some form. And you might think, why am I not hearing that? Where are all of these higher notes that you're claiming are there? Well, normally you can't hear them because they are much less pronounced. They are much softer. Remember, there are a few parameters of a piano sound besides where I hit, and one of them is how loud it is. So if I play this together with this, but I play it much softer, you almost don't hear this other note. You just hear the lower one just because it's louder, and so your ear is drawn to it. So how can I convince you that, in fact, this is happening when these upper notes normally don't sound? I mean, they sound in the sense that they're the thing that they're part of what makes the pianos sound characteristically a pianos or a clarinets or a violins, but you can actually isolate them in a few ways as follows. One of them is the reason that I insist on having an actual piano, which is that the actual piano here, again, when you strip away all of the basic machinery, or all of the complicated machinery, there is basically strings. And remember, when I hit a string, it vibrates, and vibrations go out, eventually hit you. They also hit all of the other strings. Now, one thing that makes a piano is that the strings have dampers. So there's actually two things that happen when I hit a note on the piano. One thing is that a hammer comes in from below and hits the string. The other is that the damper is lifted. And it stays lifted until I leave the key, and then it comes back down. And then the string stops vibrating. You can see those here. The dampers are above the strings. So you can see them move a bit and then move back. Don't do this right now, but at some point on this piano or any other piano, you have a look at what's happening in there. Now, if I depress a key slowly enough that the hammer doesn't actually hit the string, can do that, I can bring it to a position where it's not vibrating, but it's not damped either. And it's a basic fact of acoustics that of physics really, that just like a vibrating object sets the air in motion, vibrations in the air can set the object in motion if it's free to vibrate. So if I played this note, and there was another piano nearby on which I depressed this note would vibrate. And you can sort of hear that there's actually 3 strings on each course for most of the pianos, so I can hit one of them, and then I'm depressing it, but you can still hear the others vibrating. Now, more interestingly, I can hit the lower note, the one that I claimed actually vibrates not just at this frequency, but also at this one and all the others. And if you believe everything I've told you so far, if I hit this note and then let it go, this string is going to be damped, but this one is not, and the vibrations from this lower one should make that one sound. And likewise for 1/3. Or let me start again. Or a quarter. Again, assuming the piano has been tuned well enough for for this to happen. And conversely, if I hold the lower note and play the higher one quickly, this shows you the lower string being able to vibrate at that frequency. And also at this one, and also barely at this one. And by the way, what happens if I hit some other note that's not exactly a 2-to-1 proportion? Let's say it's a 3-to-2 proportion. Well, what happened here? Remember, this note, which is 3/2 the frequency of this one, is also at the same time 3 times 9/2, 12/2, etc. And those numbers, which are exact multiples of this lower one, of which 3 is the first one, are also modes of this string. So if you hold either one of these, if you hold either one of these and play the other, you will hear that you can think about either as a GCD of wavelengths or as an LCM of frequencies, but you will hear that vibration, and you can do this experiment on your own later. So that's one way. So really what's happening, the reason that we like to hear these kinds of combinations and don't so much like to hear is that these are actually, we are hearing the same frequencies reinforce each other. Whereas these, which are not quite the same frequency, those cause what are known as beats, which is if you take two waveforms that are almost but not quite the same and superimpose them, the combination of this, and you can prove that with some trigonometric identities, is a wave that gradually, okay, this is not drawn to scale, but the point is that you get a wave that's like the average of the two frequencies, but half the difference between the two frequencies gets louder and softer. And even though you cannot hear 440 events a second, if this note is like 110, this note is about 104, you can certainly hear 6 things per second. So you hear this wah, 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 happening about 6 times a second, and that's annoying. So that's why we don't like hearing that kind of sound. At least that's one reason we don't. So that's one example. But it happens also in other instruments than strings. It happens on pipes. It happens on anything that vibrates with, in some more complicated pattern in a sine wave, basically because of Fourier analysis. It happens with a human voice. So let's give an example, and this is going to be at least part of the audience participation of this talk. I'm going to ask you to sing with me. But it's not going to be a very complicated song. It's a song that you all know, and one with many different songs. It's the ABC song, or Twinkle, Twinkle, Little Star. Ti ta 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 ti ta tam. Okay, everybody with me now. 1, 2, 3, go. Ti ta ta ta. Okay, you're doing better than most of my audiences. You're all singing with me at the same time in the same melody, but some of you are singing ta 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 tam, and some of you are singing pa ta 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 tam. They're not following directions. Except I think a few of you, even though you can't naturally sing in that register, you were actually trying to sing uncomfortably low for your register ta ta ti ta ti ta tam, even though it's so you're in that sense you're following directions better than most of my audiences. But of course you're hissing at me because you know the reason that the distinction between who is comfortable singing and who is not is very closely correlated with if you're male or female. And if I were a female giving this talk, I'd ask you to sing in me ta da 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 da, and half of you would do that, and the other half would either do da da dee da 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 or da 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 da. It would have the same problem in reverse, but it would be a lot more obvious. So the real question is, okay, I've asked you to sing with me. Your voice isn't in my range for one reason or another, so you're trying to follow directions as best you can. Why are you singing this as opposed to da 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 or da 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 or any other place you could have started and then sung the same melody? And the reason again is that you are naturally, I didn't tell you to do this, but you're naturally singing, if you can't be exactly at my pitch, you're not trying to come as close to me as you can, you are matching the first overtone. You're matching 1/2 of the frequency. Because you're also hearing that in my voice, even if it's not conscious, and that's what you're trying to adjust to. And likewise, if I asked you to sing with me, da 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 da, and you weren't comfortable singing that high, you would sing these notes, dee da da, so that your overtones are matching as well as you can what I'm doing. And this identity, this notion that this sounds like it's exactly the same as this, only a different register, is one of the very few things. It's almost as close as we come to a musical universal. I mean, there are hundreds of musical traditions, many of whom have only weakly interacted over the years. This is one of the few things that is almost universal, which is what they call octave equivalence. Octave because in the Western tradition, this interval is called an octave. I will get to that a bit later. I realize I don't have much later by now. And in fact, so much so that we usually call these by the same name. If this I tell you is a do or a si, then this one is a si also, and this one is a si, and this one is a si. All the notes that are twice, 4 times, 8 times, or 1/2, a quarter the frequency have the same name. And so if I tell you the piece is in C major, you don't know necessarily whether it starts here or, but these are both, you recognize both of these as being the same note, unlike if a piece that started in, this is not the same key as, even though it's much closer in register. So that's another, and one final illustration. Have you ever heard, you've all heard bugle calls, like, military bugles. Or, when they tell the cadets to shut down the lights because it's night and they play taps, or when they symbolically put somebody to sleep at a military funeral and they play the same tune. The interesting thing for us about all of these very different tunes, they all use only 4 different notes. Sometimes another one. But the reason for that is a bugle is a very simple instrument. I mean, it's turned around, but it's basically it's a pipe, it's a length of air, and you can make it vibrate, but you can only make it vibrate at one of its natural frequencies. And it so happens that the theoretical bass note, like the first, I don't have the picture here anymore, but the full length of the string you can't make, so you can make twice of it sometimes, and then 3 times, 4, 5, 6. And most bugle notes are just drawn from these first, the 3rd through the 6th harmonics, and the ones that aren't will be the 2nd. And until roughly when Beethoven died, all of the brass instruments in the orchestra, except the trombone, so like the trumpets, the horns, could only play those notes also, and a few higher ones in the harmonic series. So that's why if you wrote a piece for an orchestra and you wanted the horns and the trumpets to be able to join in with a team, you wrote themes which were made up only of these notes from Beethoven's Third Symphony. Is just two different notes. There are traces of this even going as late as Mahler, and even further. By Mahler's time, trumpets had valves. Valves basically are a way of packing 7 or 8 different tubes into one length, and so you can make all of the possible notes on the keyboard, but you still have this trace of, it's not quite the same notes, but the same kind of writing where you have a very small spread out set of notes, and you just go back and forth between them. That makes it sound like trumpets or horns, as the case may be. So, okay. So let's finally draw these two threads together and see how Euclidean algorithm and harmonics come together to make our 12-note scale. And now we're finally up to our second handout. So I've said a lot about octave equivalence, and I've said a bit about the higher overtones, notably the third one. And ultimately, the reason we have 12 notes in the octave is because that's the simplest way. That's the first. That's the first choice that is close enough for hearing to believe that we have both octaves and octaves which are this length and fifths which are this length. Both the 2-to-1 and the 3-to-2 proportion. And we want to be able, if we have, some tune to also be able to play it. I mean, if it's just this tune, then okay, that's the end of that. But if it's part of a longer piece, notice again, it's a piano piece by Mozart, but he's alluding to horn sounds, even though he doesn't have to. And he's already showing what it would sound like in a different key. And then eventually he's going to go, and usually the place you want to go is like the nearest in the sense of reinforcing overtones. So if all octaves sound essentially the same, all 2-to-1, 4-to-2, 8-to-4, those sound almost the same, the next best thing is to have the 3-to-2 ratio. So almost always, if you have a tune that is based on this note, it will have the one that's the closest to it without being just another C or another A flat or whatever it is. And sometimes a few times it might seem like that's all you need. That's the example I gave at the beginning. But eventually, you need a whole bunch of more notes, right? So if this were really enough, you'd only need 2 notes to the octave. And this would work if 3 halves, if you went up 3 halves, pom, pom, and you went up another 3 halves, you would be an octave above where you started. So you go pa, tom, tom, pa. But you can tell, even without doing the arithmetic, that the distance from pa to ta is not quite as wide as from tom, pa, pom, right? If I started ti, ta, 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 ti, ta, tom, then I would not go ta, 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 ta. That's not the same tune. Unless you are writing a fugue with a tonal answer, in which case you might say ta, 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 tom. But that's a cheat. I mean, it's it's a special, dispensation. One way or the other, 3 halves squared is not 2, right? This is 9 quarters, and 9 is like 12%, 12.5% bigger than 8. Our ears can tell the difference. But you see that what we're doing here is we're saying we want a common distance, right? That's what the piano is going to provide us with. It's going to provide us with some number of with some number of quantums of musical distance. We call them halftones, but they're right. The shortest possible distance on a piano. We want a whole number of those, and then another whole number of those to get us from here to here. Now, you might think, wait a minute, that something is wrong here. We are multiplying ratios, right, to know how much it is to go up 2 octaves. You go up 1 octave, that's 2 to 1, another one that's 4 to 2. That's, go another one, it's 8. It's not 3 times 2, right? So what we are looking for here is a solution to the equation 3/2 to the m equals 2 to the n. That doesn't look like it's a question about commensurability. The reason it is that you can take logarithms, right? I mean, that's the way to convert equations in exponents to ordinary multiplication, right? So what we want is the log of this to equal the log of that, and that means that m times log of 3/2 should be n times log of 2. It doesn't matter in what base you're taking the logarithms. This is still going to work. And now you see that it's a commensurability question. We want to find a common measure that lets you measure out both the log of 2 and the log of 3/2. And log of 3/2, as we just found out, is a bit larger than log of 2. So in our first step of Euclid's algorithm, we find, whoops, that's too high. So in our first step, we'll change finding the common distance between the common measure of this interval and that one, again, in that logarithmic sense. We'll convert that to a common distance of this and that. This being what you get by taking this interval and subtracting this one. Okay, now this one we'll bring back to here. So we're looking for a common distance of these. And, well, okay, so we measure one of them and we are left with this difference. This difference, if you've been keeping track, is 9/8. Or alternatively, you could say, well, I just keep going. And this is what's on the other hand. Okay, so the other handout, the one page. On one hand, I gave you the answer by looking at the continued fraction expansion of log base 2 of 3, which is basically the same question as this, because, right, this is, if this were the case, then 3 to the m would be 2 to the power m plus n. So I've already done the first step of Euclid's algorithm by going from log of 3 to log of 3 minus log 2. And then I give you the next few steps in the continued expansion, and continued fraction expansion. And then I show you what happens if we start from, let's say, middle C, and then we go up this interval, the 3 to 2 ratio. We find that this one is too high, and so we bring it down from this D to this one, and then we keep going. And we have made a very common, almost as universal, scale known as the pentatonic, which is just fancy Greek word for 5-note scale. And lots of tunes all over the world are in this 5-note scale. Arirang from South and North Korea. Okay, this is the one note that's not. I mean, anybody watch All in the Family? Lots and lots of tunes that are all or mostly all from this so-called pentatonic scale. And why did I stop here? Why didn't I keep going? Because the next note, that's the first one that's dissonant. It's the first one that's close enough to see that for most of us we begin to get bothered by the beats. So this is what happens remember I was doing Euclidean algorithm. I started from these two intervals. I made it these two, and then this one and that one. And then I lay out, and this is the first time that you get that. So before we hit that, we've only found this approximation. If this interval really were the same as all the others, this would mean that we have gone up 5 times. 1, 2, 3, 4, 5. And that would be the same as going up 3 times here. So doing the arithmetic, this would be 3/2 to the 5th. So 0, 1, 2, 3. Oops. 4, 5. Roughly equal 2 cubed. That's not quite right, because this is like 243 roughly equal to, right? So this would mean 3 to the 5th equals 2 to the 8th, roughly 256. That's closer than we were before, but still not close enough for our ears to believe it. So we keep going. We accept this as another note, not the same as this one. And then we either keep going, or equivalently, we take this other note down the same interval. So, and now we have found, in a different order, the standard 7 white notes on the piano. The previous one, the pentatonic scale, even though I started on C, if I started on D flat or C sharp, I would wind up on the black notes. There's a famous Chopin etude for which the right hand only, the left hand is allowed to do other things. He writes sort of the entire right hand part, with one notable exception, is just on the black notes. And those are the pentatonic scale. But now we have the normal 7-note scale that almost all of Western music and a lot of other music is written around. You can play through the whole beginning of this Mozart sonata. So far I haven't played a single note that's not white. That's the only one. And this is common. You can play lots of, sorry. That's the first note of that Bach prelude. And then he goes off to another key, and then he basically rearranges and says, okay, I'm going to use a different set of 7 notes. But lots and lots of tunes and whole pieces are written just with, either the white notes or the white notes transposed to a different key. That's the so-called diatonic scale, and it's so universal. That's our basic notation for musical notes and intervals. So notes C, D, E, F, G, anything that's not one of these, we describe as being, remember, just above a G or just below an A, or just above an F to an F sharp. And likewise, intervals. This is an octave because you start from this first note and second, third, fourth, fifth, sixth, seventh, eighth. But music theory started out being first in Latin and then Italian. And so ottava, or in Italian octava, was the 8th. In other languages, say septima, sesta, quinta, and so forth, you say 7th, 6th, 5th. And so this one is the 5th. Of course, the problem is we started counting at 1. And that means if you go up an octave and then a 5th, since I told you that octave means 8, 8 plus 5 should be 13, but it's not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 8 plus 5 is not 12. But these numbers are off by 1. Octave is distance from 1 to 8, so it's a distance of 7. 5th is a distance of 4. 12 is a distance of 11. and 7 plus 4 does equal 11. Yeah, likewise, if you ever, had to do musical counting of rhythm, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. It should be 0, 1, 2, 0, 1, 2, 0, 1, 2, 3. So like the strong beats are the even numbers instead of starting from 1, but it's much too late to fix that. But it's not too late to fix the scale. Okay. That's what would have to be another 3-to-2 ratio if we actually had a perfect 7-note scale. So that would be going up 1, 2, 3, 4, 5, 6, 7, being the same as 2 to the 11th, but that's not right, because that's 2187, this is 2048. Again, they're too far apart for our ears to believe that they're the same. And in fact, this annoying interval is known as the tritone, because you get it by going up 3 whole tones, but it also had a much more suggestive, evocative name in music history. Remember, they mostly wrote still in Latin, and they called this interval, you don't need to know much, if any, Latin to guess what this means. I mean, in musica, of course, is in music, and diabolos means devil. It's as if the devil himself managed to insert, something diabolical and sinful and wrong into like the perfect Pythagorean system of the music of the spheres, and sorry. I mean, this is sort of like, tritones have a place in music, but they have to, in Western music, they're very carefully controlled, That's a tritone, but that's okay because Bach knows that it has to go back to the perfect, 4th, 5th, 6th, 8th, 10th harmonics of whichever note they're the common overtones of. Now, one thing we know about this tritone, at least if you believe in the piano intonation, is if you go up a tritone 2 times, whoa, that we know, that's an octave. So that means that the tritone is whatever interval x, whatever ratio x to 1, such that if you go up that interval twice to get x squared over 1, that's equal to 2. But that means that x is the square root of 2. And the square root of 2 is infamously irrational. It's the same diabolical irrationality that first, as another legend of Greek math goes, the Greeks honored the discoverer of the irrationality of square root of 2 by making him an unwilling sacrifice to the gods. They dumped him over overboard. And on the other hand, this seems to give us the answer that we want. Because on the one hand, that's a tritone. On the other hand, we got it by going up a fifth 6 times. So if we go up a fifth 12 times, 3 over 2 to the power 12, we should be up an exact number of octaves. And in fact, the piano, another reason for having a full-length piano is that it's just long enough to do this demonstration. It starts from the lowest C on the piano. You go up a fifth once, twice, 3, 4, 5, 6, tritone, 7, 8, 9, 10, 11, 12. That's another C. 1, 2, 3, 4, 5, 6, 7. So that explains why we have 12 notes to the octave. It's the first time where most of our ears are willing to accept that you have found the common measure of log 3 and log 3 halves and log of 2. Now, of course, this is a lie. You don't need to figure out these numbers. I mean, You don't need to work out what 3 to the 12th and 2 to the 19th is to know that this can't possibly be correct. Because this is an even number and that's an odd number. I mean, if this were correct, we would, after all, have the square root of 2 as a rational number. But it's the first time that it's close enough. And now I've been behaving as if these ratios and frequencies are these exact, Platonic numbers. But, this is a real physical instrument. The three strings on a single note aren't tuned exactly the same thing. The 2-to-1 ratios aren't exact. I mean, they're close enough that, the string picks up the resonance, but it's not an exact 2-to-1 ratio. When it comes to our ears, there's additional, spreading out of the frequency. So yeah, it overlaps enough for our ears to accept that it's the same note. But there's a lot of fudge that can be spread out over the 12 notes of an octave. That's what's known as tempering. When Bach wrote the well-tempered clavier, it was a keyboard that was tuned so that you could play it in all of the keys, even though if you insisted on making this exactly 3 halves and this exactly 5 halves, then by the time you got all the way around to F sharp, you would have some really ugly sounds for playing the F sharp major piece. But if you tune the piano so that instead of having an exact 3-to-2 ratio, you have a 2 to the power 7/12 ratio, which is 1.498 or something, that's close enough to 1.5 for you to accept. So that's what actually happens more or less in each one of our pianos. And this finally is why we and almost all of Western music divide the octave, if we're going to divide it into equal parts at all, into 12 parts. We have basically carried out a continued fraction expansion, stopping at this notional 2-note scale, at the pentatonic scale, and then at the 7-tone diatonic scale, before finally settling on the chromatic scale, where for the approximation that's given by the piano, if you get to this note by starting from C and going down 4 steps to an A flat, or going up in the sharp direction, it's the same note. If you're a violinist, you know that A flat and G sharp can mean sufficiently different things that you have to be careful about where you put your finger to tell which one is which. But for keyboard and anything that is unfortunate enough to have to play with this very approximately in tune device, you have to pretend that A flat and G sharp are the same. So I think I've given you some notion of how these various threads are connected, among other places, by the intonation of a piano and the white and black note pattern. Of course, I've completely suppressed. I've given you just factors of 2 and 3. What about 5? Well, it's a happy accident that if you go up 5 to 4, which is a consonant enough ratio, 3 times, this is a rather strange sound, but it does seem to span exactly an octave with 3 of these ratios. 5/4 cubed is 125 over 64, which is almost exactly 2. The difference between 125 and 128. It's enough for our ears to notice that something is not quite right, but it's close enough that by the time you get to Beethoven and Brahms and Schubert, it's actually quite common for a piece to go from C to E to A flat back to C, and to use this division of the octave as a as a new organizing principle that people like Bach and Mozart didn't really have. So by a nice coincidence, parts of 5 work also. Parts of 7 really don't. And that's a different story. But that already shows us that there is some, we understand very well simultaneous approximation of 2 numbers, like how to use the Euclidean approximation, the Euclidean algorithm, rather, to find an approximate or exact common measure of two intervals. If you have three intervals, or three musical intervals, like the log of 2, the log of 3, and the log of 5, we want a common measure for all of those. That's harder. And in fact, if you give me a sufficiently long list of numbers, then we get into some really interesting mathematics involving simultaneous rational approximation and mass reduction and things like that. But OK, I'll leave that to some of your mentors who might be advising number theory projects to go into, and just be happy that by a nice coincidence, our ear's accuracy and the arithmetic of these numbers make it possible for us to find also the overtone of the 5-to-1 ratio in the same system of 12 notes to the octave. I'll just finish maybe with one additional nice coincidence. So if you go up 1, 2, 3, 4 steps, you're almost at this note. That's the exact 5-to-1 ratio. Maybe better on this note. I'm sorry. The 5-to-1 ratio is not quite, but the point is 3 halves to the power 4. I was trying to get to a point where I can go up 4 times, and you can actually hear this resonance the way I was showing before. But that's actually not as common. Oh, this one works. Anyway, 3 halves to the 4th is 81/16, which is really quite close to 80/16, which is 5. Close enough that there's a special name for it. This is the syntonic comma, as the one we had before was the Pythagorean one. At any rate, yeah. So, and this, of course, is something that shows up in music all the time, so much so that for a while it seemed that musicians weren't aware that these were 2 different ways of getting from C to E. Anyway, OK, by now I'm sure I've gone over time, so thanks for your patience, and good luck again with your own research.
What about improvisations?
Well, first, are there any questions before we get to improvisation? No.
We have time for some individual questions afterwards.
OK. So yeah, one thing that was not explicitly mentioned in the introduction earlier was that one thing I do is, well, I guess nowadays people call it mashups, which is sort of what I was suggesting in the beginning by playing together and so, of course, if I'm going to, so that I had a chance to think about in advance. And so if I'm going to improvise, how do you know that I'm improvising and not just doing something else that I either figured out in advance or am, copying a Schubert piece that I'm hoping none of you recognize? Or so there is something that the computer scientists have taught us about protocols. That is to say, we design a protocol in a rules for interaction which let me give you some confidence that I'm actually improvising, that I would have a hard time doing this repeatedly if I were not actually improvising enough, if I was playing some pre-existing piece. And that is for me to be constrained by having to improvise on themes that you're going to give me. So I'm going to ask you to suggest, let's just say 2 or 3 themes, so I can try to make something like a fake sonata movement out of it, rather than just an overture of one thing after a second, after a third. And please have it something that I have a chance of knowing. Don't tell me like some tune from Hamilton because, first of all, I haven't seen Hamilton, and second, most of the tunes are actually raps, which are, might have interesting, words, but aren't much to play. So, and it should be something that other people here are likely to recognize too. I mean, don't tell me, Mozart's 25th Symphony, because even if I know it, it won't be as funny to hear, oh, well, this might be Mozart's 25th, then again, who knows? So, okay, any suggestions? Yeah, back there.
Do you know like the Me Channel theme?
Okay, evidently various people here know it. I don't, but maybe you can sing or play or something. Or... Wait, so do it again? Okay, sing it together, but in octaves. The problem is I'm hearing something like this. And the reason I'm hearing this is that you didn't, you all started roughly at some low note, and then you were all very insistent that you had the right key. So maybe if one of you can play a version of it for me that I can try to work from, because unless you really want me to improvise on. Anybody? Or can you play it on your, find it on YouTube or something? Anybody? Or can one person sing it?
Do, mi bemol. All right, I'm super slowly.
Do, mi bemol, da, tom. Okay. Dom. Something like that? No. Okay. Okay. I can't hear while you're laughing. Sorry. Okay, try. Okay, that's a lot of notes. Sorry. Can we pretend it's that? Okay, so that's one. And okay, so this means that. Okay, and something else? Yeah.
Let's say something slightly easier. Ode to Joy by Beethoven.
Oh, so what I was playing before? Yes. Okay. 3, 3, 4, 5, 5, 4, 3. Okay. So Ode to Joy and Ode to, what was the one called? Ode to Me? And maybe one more from. Okay, way back there. The what team? Everybody's clapping, but I can't hear it.
The Avengers theme.
Avengers. I should know that one. How does it go? Da da tom, da 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 tom. Something like that.
Yeah, that's definitely close.
That's definitely what? Tim tom ti ti di tom ti. Okay.
Wait, this is short answer. So this one.
No, that's a different one.
That sounds like James Bond. That's a different tune entirely, I mean, right? Okay, so it's this, right? Something like this, right? Okay, I mean, I think I have enough tunes to start with. So let's see what happens.